Alrighty. Yeah, I didn't do my cardio. So I probably shouldn't say lunch/cardio on that bad boy. I will need to do cardio. I have to cut my dinner short. Do cardio in the evening. Oh, and I have MAT. Fuck. Well, I guess I'll have to just do my best to do dinner/cardio. And I'll hop on tonight for evening stream. But I might be a little bit late because of the cardio. I didn't do cardio during lunch. So, anyways. Alright, look at this. We're writing a bunch of C. Kill that. Okay, so we had this load logic we needed to implement. Logic around loads and stores. So we still have to implement that, but I want to get into running the simulation. So this will be in its own little scope. And we're going to open the file and read a line. Parse the line and handle the line. It's a high level sort of thing. Can we maybe extract this into a helper that says validate values? Or we could just pull it all out and just have these be returned. This whole thing, you say parse args, and this is all stuff for argument parsing up here. So func, right and go, parse args, and we'll do that. And I want this to be a struct. So we'll have a struct args, args t type def, and then in the args we're gonna have set bits, basically all this. We're just gonna pull that up here, dt that, repeat that here, here, and here. Oops. So that gives us our args struct. Now we can just say args t args is equal to the initialization of this stuff, and then we don't need the types here, so let's delete all that. And then I think you have to put a period in front of here to make that valid. Oops. Then I think these need to be commas instead of semicolons. So that gives us our arg struct initialized appropriately. And then this will be, oops. So we're going to return args t. And we also need to receive our args, argv, argc, no, argc, argv, int argc, and a char star argv array. That, I think it's an integer, right? Yeah. Okay. So that's correct. We don't need the scope anymore because that's kind of like enforced by the function. So here opt, that's fine. And then we're gonna say args args.sepits, args dot that, args that, that, and then we'll just oops, do that, and then down here return args. So I think I can do that, and I don't have to do a pointer. I think C will allow that. So then I say parse args, argc, or argc, argv, and it gives us back our args. And I can do auto here, auto. So I'm using C++ or C23. Initialize int. Why does it say that I'm initializing int? Oh, because my Clang stuff is not set up here. I need to find, maybe if I jump over to KNR, and I'm gonna find iname .clang, I think, something. Oops. Cat chapter 08 clang d dot clang d. There we go. CP that into source GitHub JSON. Let's see. Where are we at here? CSAPP labs cache. There we go. All right. So now if I go back over here and hit that, it figures it out. Same thing here, auto. Here we need to say, hey, this is going to be args dot. Okay. And then same thing here. Where else can I use auto here? Val. I can say a long val here, but string to long returns a long int, so I can say auto here. Delete that. Just doing some code hygiene here. I need the char star there. Stir len is going to give us our size t anyways, so we'll just auto that. And oh, it comes back unsigned long. Stir len is a size t. That was a size t. Maybe a size t is ultimately unsigned long. Okay, what else we got here? Looks good to me. Can I do something like auto here and say args t like that? No, that's more of a goism. Can I say auto here, like auto opt? No, because it has to be that. Okay. What about over here? Is there anything here? No, that needs to be there. Everything's good there. Print summary. That looks good. let's see, on a machine instruction level in x86 64, if in C I return a struct with a number of fields in it, not a pointer to a struct, how does that value get returned since it cannot fit in EAX? Hidden pointer argument. I've seen it do that before. Or I've seen Rust compiler do this before. And I think I've seen C do it. I forget the name of that. It's like Rust does this as an optimization, so you're not like returning, you're not doing a bunch of copies. It's the 8th time this garbage truck has passed by my house. Alright. So we're going to start on the simulation. We're in the simulation. Oh, no, sorry. I meant start on... Yeah, running the simulation. So we have to open the file, fopen. And it's going to be args.filename. And this is going to be for reading. So we'll say R. And that gives us back auto file. And then we need to make sure to close the file. Fclose file. The end. So while one, we'll fill in that condition at some point. We're going to say read a line. How do you read a line? And I'm just gonna rely on chat. How do you read? Set up a loop in C that uses fopen F close to open. Open a file for reading and read each line and do something with that line. Okay, okay. So we got, oops. If FP is equal no, then we can return exit failure. So we got our buffer, 1 bit shift over 10, and then we say f gets. That's what it is. That's the thing. While f gets into buffer, size of buffer, file. So I'm gonna do man 3f gets. If gets reads in at most one less than the size characters from the stream and stores them into a buffer pointed to by S, reading stops after an EOF or a new line. If a new line is read, is stored in the buffer, a terminating null byte is stored after the last character in the buffer. I mean, I don't think that's the right way to do it then. I think you need to subtract 1. Get line, okay. They have to free the line at the end. Get line reads an entire line from stream, storing the address of the buffer containing the text into line pointer. The buffer is null terminated and includes a new line character if one was found. If line pointer is set to null before the call, then getLine will allocate a buffer for storing the line. This buffer should be freed by the user program if getLine failed. Alternatively, before calling getLine, line pointer can contain a pointer to a malloc allocated buffer n bytes in size. If the buffer is not large enough to hold the line, getLine resizes it with realloc. In either case, on a successful call, line pointer and n will be updated to reflect the buffer address and the allocated size respectively. Okay. I like this API better. Okay, we kill that and kill that then. This needs to be file. If I man 3 f open, or maybe like get line, it calls them streams. Yeah, and it actually uses the variable name stream. Oh, there's an extra. Oh, that was just exit. Okay. So why does that not work? Undeclared identifier man get line. So this is part of standard IO. That should work. I have standard IO here. Use of undeclared identifier get line. Make. It should be there. I don't know what to tell you. Man get line. Is there like a... Do I have to do one of these? GNU source. Okay. Pound. Fine. I think I can say default source. Yeah, default source works. Make. Okay. All right, so we read our line. Parse the line. Let's do... cat traces Dave. What's some other ones here? Trans? No, it's transpose. YI2. So that's load and stores. Load and stores M's. YI.trace. Let's store an M. Let's do long. Plus given this text input for a file, write me a function that will parse a single line into a struct. And I'll define the struct that I want up here. Actually, no, I'll define it right here. Struct line. It's going to have type, which is an enum, line type, let's pull this out of here. I think that's okay. Enum line type so we can have a unknown load a store and a modification. Okay. and then I need to type def this. Type def that as a line type t. Oops. Oops. I need to do it like that. Oh, that's a cache line versus a file line. Input line type. Okay. So as a type, it has an adder, which will be uint 64t, and it'll have a size, which would be a size t. Okay, so that's going to be our struct definitions. I think I'm going to start pulling this out as a separate section here, and we'll say input parsing. Okay. And then here, yeah. Let's go ahead and grab all this, give it here. Okay, we got a parse line. Okay. Okay. And then I just want to review the parsing logic that it generated. So if the line is null or out is null, then return -1. Skip leading white space. Just advance the pointer. Parse the operation type. So we say, hey, line, go up 1, dereference into car op. That'll set those. And then skip white space for your op and address. And then parse address and size. Format is hex decimal. So we have a char star end pointer. Stir to unsigned long long. B16 to the end pointer. Okay. If end pointer is equal to line, then we weren't able to parse, or end pointer is not at the comma, then we have a parse error. Otherwise, you say, hey, the line is now equal to the end pointer plus 1 because we want to skip over the comma, and then we convert that thing base 10 into our size, and then that should be fine. Okay, that's pretty good. Pretty good. What is it saying? Is space. Oh, okay. I'm gonna need to have some library functions up here. Let's see. Man is space. C type. Okay. C type. Okie dokie. Everything looks good there. Let's go ahead and hit make and let's run it. csim. Actually, csim. Oh, we're running it over here. Like this. No such file directory, traces. Sorry, traces / Dave. And if I cat out that, its type is 1, which I think is right. Store, load, store, yeah. Adder is 10, 18, 20, 28, 50, all 4s. Okay, looks like it's parsing correctly. Let's do the long. We'll just grab the head and say head of traces long. Sorry. Can I do 2 and 1? What's going on here? Oh, because I'm just doing cat instead of the. There we go. Long head N20, and then we'll do cat of this. Why not? Makes it simpler. Alright, so let's make this a little bigger. Store, load, store. Oh, because we got 1, 2, 3, 4, 5, 6 lines there. So it's it back up. This would be -6, which would be this, and then this -6. 14. So store, load, 1, 2, 3, 4, 5, 6. And then it goes load store, yep. And we got 1, 4, 4, 8, 8, 8, 4, 4, 8, 8, 4, 4, 4, 4. Looks like it's parsing correctly. It's getting all the addresses correctly, it looks like. Alrighty. So now we gotta do our little simulation. Okay, so reading trace data from file, parsing it. I lines can be ignored. Are there any I lines? I might get like an invalid action failure on some of these if there are I lines. Yeah, let's go up here. Let's add another type called instruction. And we'll handle that here. Say case is going to be I. Then this will be instruction. And if we grep for I, just yeah. So what file is that? R, say L, traces trans. So right now if I run csim on traces trans, it'll blow up with parse error. So I have to save this. So we get the line type down here for instruction. Then in our case here, we have to handle it. Line type instruction. And we'll just say note instructions said to lab instructions said to ignore this. Alright, make it, and we'll rerun. Yay, we didn't blow up that time. Cool. Alright, so if we go to here, I don't need this printf anymore. I'm pretty confident in, or maybe we do this as verbose, because we do have that verbose flag, right? I think we have args for verbose, right? I think we do. We do not. So I think I can do like v like that, and then this can just be a bool verbose dot verbose is equal to 0 for false. I'll say false, and then here we'll just say verbose is equal to true, and this will be v. There we go. And down here we can say, hey, if args, args dot verbose, then we printf. So make, and then dash v, look at that. And then if I do it here, that'll work too. Yep. Cool. And I think it's going to be the same thing here with these printf parameters. I don't really like having those printed out. Make, unless it's in verbose mode. Cool. Alrighty. So now let's start implementing this simulator stuff. Just want to make sure there's no to-dos here. I don't think there is any. I would like to factor this out. Taking actions data important free. This whole thing, it'd be nice to factor it out as a simulation run type thing. So we go up here to our simulation section and void run sim, and we just paste that right there. We no longer need this block here. And we're going to need to take in args. T, args. I think that's in, of course, the simulation. Should be a SimTS. SimT pointer S. And then this needs to be an exit thing. And I do have exit helpers up here that I wrote. One's called exit usage, the other one's called exit message. Exit P error. It's another one. P error S. Anywhere I can do P error, I can now replace that with exit P error. Delete that thing. Delete that. Like that. Okay, exit P error, P error. There's only one? Oh, okay. This one is an exit message. Exit message. And we'll give it the parse error. I don't need that. Give it a new line there. Exit message. Where's this thing being used at? Nowhere? Thought I just called it. Did I typo it? Maybe I typoed it. Yeah, too many S's. And then exits. Just find everywhere we're doing exits. Those are cool. Those are fine. Here we go. This be exit message. Invalid action. And we don't want to do that. Oh, and I have to, if this is going to be part of the sim, then all of this stuff here with parsing, input parsing, needs to be above that. So that will be somewhere here above the simulation, like that. Okay. So make. Okay. Let's do -v. Okay, it's not running because I didn't do run sim s and args. Oops, make. There we go. It's doing stuff. Let's go up here. We now need to do our last to do, which is in the sim logic here. which is the whole crux of the simulation, is in the load. Okay, well, if we want to use the least recently used eviction policy, we need to have some way of tracking when it was used. And I think a heap data structure is a little bit overkill. So I think what I might do is just assign some type of like counter into the cache line. And then when I'm scanning the set, I'll just find the one that has the least value and evict it. And every time we do a lookup, we'll set its counter to the global counter and increment it. So we need some type of global counter as well. But that would be part of the cache struct, I think. Or the sim, maybe? Or maybe cache struct is the right place to put it. No, it's probably should be on the set because it's the least recently used element of the set. So set t is not going to be a struct. It's not going to be a line t pointer, which kind of fucks up our allocation strategy a little bit. Well, let's fuck it up. Okay, so this fucks up our allocation strategy here. Or not here. And there's no compiler errors, which is wonderful thing about C. Is that it don't give a fuck if you fuck up your allocations. I wonder if this will segfault. It should, ideally, because it's going to compile make clean, make No, you have no sense of it fucking up. Okay. Let's take the V off. Well. I have to do like a new set and a free set type thing, and then delegate to those. We'll say set T, new set. I don't think I do need lines per set. Yeah. And block bits. So that's our set. And a cache is just an array of sets. So here, now when we're allocating our cache, we're going to say, hey, that's how many we want. And it's going to be the size of set T. No. Yeah. So we say, hey, this is how many sets we want, and this is the size of the set. And the size of the set, that's great, that's 0 initialized, but we still have to go through each one of those and create its lines. So we say for, we'll say auto I is equal to 0, I is less than 1. We'll say num sets. Assigning set t. Oh, we want a new set and then we want a pointer to it, but I can't do that, can I? Yeah, it's an R value. Well, shouldn't new set return a pointer anyways? Yeah. So assigning set t. And a set t. Oh, because we dereference this here. So we get our pointer, create our new set. Well, I can do that. What'd be really nice is if in C tests you could like set like, okay, this is the memory range that I want to allocate, and I don't want to go anything beyond or before that range. Just to verify that you don't have out of bounds accesses. I think there's a way to do that, at the very least with protections. It's certainly possible. I know it's possible, but I don't know exactly how to do it. But it'd be nice if like there was a standard C testing framework that just did that for you. Can't believe there isn't. Like the Google test thing is a C++ library. It's not even a C library. I guess you can test C code with it. Alright, I'm a little shaky on like the memory layout here because we have a lot of pointers and a lot of stuff going on here. So we have a set. A set, when we new it up, is just this struct that has the use and a pointer to the lines. And lines get allocated entirely separately, and that's the lines per set times the size of the line. The line is just a line struct. So that's our set, and we have a pointer to it. So already we have two pointers. We have the set, the pointer to the set, and then the set has a pointer to the lines array. So it's already like, as far as like locality, is not taking advantage of a lot of the locality stuff. But it's a simulation. It's not really like high performance here. So then we have this A, which is a pointer to a bunch of pointers to sets. So now this is our array of sets that we're going to point to. And then they're going to point to other lines arrays. So now it's two levels of indirection, or two levels of pointers. So we have our pointer to the array of pointers, and then those things point to our set, individual sets, and then those have pointers to the actual array of lines. And then last but not least is the cache itself. Oh no, that is the cache itself, which is a pointer to the sim. So when we have that sim pointer, it points to the sim. The sim points to an array of pointers. Those pointers then point to individual sets, and then those sets have a pointer to an array of lines. So we're all over memory right now. We are not in any form of contiguous memory here. I could do better. The problem is that the size of this cache is not known until runtime, which kind of makes things a little bit more difficult, because while we can still allocate the memory for an array, each array element doesn't know its size. Like if a say a set, for example, this guy here, if a set is just the uint8 for using it and then the array right next to it in memory without the pointer, it would have to know that at compile time, the size of the array. You could do a variable length array, a VLA, but I don't think that'll work in this situation. So I'm just going to let it do it with pointers and not worry too much about it. This is what we need to focus on here. I wanted to walk through that though just to make sure that I had everything wired up correctly here. And here with our sim, we allocate the sim itself, and then we allocate this number of sets and the size of the set. And then for each set, we do up a set. So let's go ahead and make that and run it. And it looks like it's fine. The thing is that we also need to do this loop down here and compute the num sets. So num sets needs to be up here. So maybe the cache can store that. Does that complicate things? I think it actually might be better to do it that way. So here will actually be, because we'll have a constructor for that separately, yeah. And we won't have to reach into the details here. Yeah, I actually think I might prefer that. It might not be as optimal, but code organization, I think it'd be a little bit better. So we're gonna have, similar to we have new set and free set, we're gonna have new cache and free cache. And I'm just going to rename all the sets here to cache. And we'll just comment this out for now, because we haven't really looked at what it's going to take to implement this. Oh shit, I forgot free can error out. No, it's a void. Okay. Can't error out. Okay. So this thing now needs to be a struct. So it's going to be a struct called cache. And in there, we're going to have sets, which is going to be a pointer to set t. And number of sets, which can just be an int or whatever it is, along. And down here, we're going to store it as a cache t pointer. So we bring that pointer down there. So when we do our cache here, we're going to have one size of cache t. And yeah, that's correct. And then we have to do our sets here. So these are going to be sets. And we could do this loop, I think, now. Here. So here we calc up S number of sets, size of that might actually be better. Not much, because there's still pointers in there. So each line I don't need a constructor or a destructor because lines are elements of an array which will be allocated and freed independent of the lines themselves. So this guy, very simple. Now a set does need a constructor because it has some metadata associated with itself along with a pointer to the array of lines. So we go in here and this is where we calc up the lines by saying, hey, whatever the size of the line is, multiply that by the lines per set, and s.lines is going to point to the first element there. And if that's null, then we error out. We don't want exit usage here. We want exit message. So this is a misuse of that. Exit message. Let's go and fix these. Okay. That is usage. Usage. Yeah, usage. Okay. So that takes, wait, let's go back here. So that creates the set and the lines for the set. Everything's happy now. We have a pointer to that memory. So we can then free that later. We can free the lines themselves, and we can free the S that we allocated. So sets and lines are now a nice little package we don't have to worry about. Now caches have inside of themselves an array of pointers to sets, and how many of those. So when we created a cache, the first thing we need to do is, well, allocate the memory for the cache, which is just this little struct here. So it's a long and a set t pointer, which is going to be two 64-bit words. We handle our error here, cache, and then we compute how many sets we actually need in our array. And then we set that into our field here. And then calc is going to say however many sets that we need and the size of the set itself. Now that's going to be the array. Actually, the array is the size of the set pointers because we're putting pointers in there. So it'd be more like this, because each one of those is going to be a pointer. So a more reliable way of doing this would be to go to the field. So that would be size of C sets sub 0. But I don't think I can do that because that's going to read from the first element. But I can do it as set t pointer. In C, I have a variable that is a pointer to an array of pointers to structs. I want to allocate space for this array, or this pointer variable. How do I do that? How do I do that reliably without mistaking the size of wrong type? Always allocate using dereference type, not the spelled out type. Okay. Happy to do that then. So let's find everywhere we have size of. Wait a minute. Sorry. Size of. Size of. Can we say. S dot lines dereferenced. Sorry, S ampersand lines dereferenced. I think this has the greatest precedence. Let's check our precedence table. See precedence table. Arrows should have very high precedence, yeah. Above unary. Okay, let's go to our next size of. So that's fine. This needs to be size of C sets dereferenced. Then this one is fine. Okay. Okay, so now we have, okay, we take the size of, and this can't be lines, this needs to be set lines, cache sets. So this will be the size of C dereferenced accessing its sets member, and then dereferencing that to get the element, which will be a pointer type. It would be a pointer to sets. And then we're going to new up a bunch of stuff and assign them in there. Yep. And then when we free cache, we go over all of them using this member that we saved off earlier. And we grab this set there, dereference it. We say, hey, free that. Then we also need to free our C sets memory. So that was like a little array of pointers that we need to free. And then we need to free our C finally. Okay, so that's all of that. So the cache is now fully initialized. Our sim has a pointer to a cache and some of the reporting data. We allocate up the size of the sim t and then we can just say s cache is equal to new cache, give it set bits and lines per set, and that's all it needs there. And then here we don't need to do this loop, but we do need to free that. No, we need to call free cache on scache. So free sim calls free cache and frees up the sim. Free cache calls free set on all of its sets and its array and that, and then free set goes in and frees up its lines and its s. Okay. So if we look here, we have 2 calix and 2 frees. Here we have 2 calix and a new O of n newing. We do the O of n freeing and then 2 frees here. And then here we have 1 calix and 1 new, and then 1 free cache and 1 free, which seems to be correct to me. But I'm going to do a memory layout here. Actually, you know, I'll just trust it. I think it's fine. So now we gotta handle our load. So what do we do here? We say, hey, well, S cache. We can have a method here. Say method. I mean, it's a function in C, but it's basically a method. So it's going to be a check how much time I got. I got 30 minutes before I have to drive to MAT here, and that's important that I leave. So let's try to get something at least passable for the first trace before I leave for MAT here. So trying to think how I want this to behave. I could do all the logic and load here, and then if I feel like it needs to get moved into somewhere else, I can do that. So here we say, hey, cache. We need to figure out our location in the cache. Select sim. So here we're going to say select, what do they call these things? Shit. Set. And we give it the cache, S cache, and we give it the adder. And this will give us back our sim. And we'll say auto here and give it a semicolon. Okay, so that's basically what I need here is a select sim thing, which will be on our cache. So I'm going to grab this guy, and I think it's going to be a sim t pointer, select sim, given the cache and an adder, which is a uint 64t. Then we need to split the adder to get the bits to index into. So bits, cache has a number of sets, but I need to also store the set bits. There we go. So you can hold on to those. So now I could say, hey, okay, there's the way I remember it is the tag is in the middle, right? So there's three things here. There is, oops, block bits, tag bits, and then why did I say select sim? Select set. There we go. Set bits. I think that's the way it works. Let's go back to the handout. Can I pull up the handout? Open up. I need to kill my chat GPTs here. Open up the PDF, star.pdf. Do they have the layout here? Oh, is that it? No. This transpose stuff. don't see it. Well, we have the book, so we're gonna open up downloads, I think it's under. Computer or CSAPP. There we go. And if we go back to the cache memories area, we can scroll through here. Here it is. Valid tag, but T bits. The T bits are the highest order, and then the set index, and then the block bits. Okay. So let's go back here. I got these mixed up. Set bits go here. Tag bits go up here. I thought it was reverse. So we need to pull out those cache bits. We also need to know the tag bits. So if you get set bits, lines per set, and block bits, do we not have tags? There's not any concept of tags? There's not even a fucking mention to tags here? Well, I'm a bit confused here. Let's open up the book again. There was, here we go. Tag index bits, index into the set, and offset bits. Maybe we should just assume 64 bits, so everything else is in the tag. I think we should do that. So the cache needs to store all of the information now. Set bits, number of sets, block bits, and I guess lines per set doesn't have any impact on the we do need to pass in block bits here. So that goes into here. Say long block bits. And then I'm going to store it here. What is this? Expected semicolon. No member block. Well, that's because I typoed it. Oh, I had a long here? Why did I do that? Oh, I must have... I don't know why I did that. There we go. So we can shift off all the block bits. So we say, hey, adder, you're going to shift off C block bits and this will be our set IDX. And then we want to get rid of the tag bits as well. So before we do the shifting here, which will be now on set IDX, this needs to be a right shift. So adder here, we're going to right shift over the total of, so we have 64 bits minus our block bits and our set bits. Or we can just say size of, or sorry. Well, we know it's 64. Fuck it. I don't need to. Okay. People hate my edge numbers. So size of you adder times 8. There you go. I mean, that's the correct expression, but it doesn't like, so let's do maybe that to force precedence, just so that the warnings go away. So adder is going to be left shifted. We're going to take the size of the adder, multiply it by 8 to get its bit length, and we're going to subtract off the set bits and the block bits which we need. We're going to shift everything else over to the left. That's going to so this is going to be bad bits, tag bits, and then we can shift it right by tag bits. And since adder is a uint, it won't do arithmetic. And we have zeros there anyways, so we're fine. So now we have our set IDX. Actually, this needs to be set IDX here. And since we're doing that, we can just do a shovel here. And actually adder is a copy, so we can do it against adder. We don't have to create a new we can do that. Adder that. I think we know multiplication is a higher precedence than, and size of, I think we know. See precedence table. Like size of has the highest precedence, and then multiplication, and then subtraction. I think we know that. I don't think we need to have the extra parentheses there. And then here is drop block bits to compute IDX. And now we can say, hey, C, go into, and I'm going to say if, no, we don't have that. Can I do like a global here? Say bool verbose false. And then as soon as we get our args parsed, we set that. Say verbose is equal to args.verbose. And now in my logic up here, where am I at? Simulation, here we go. I can say, hey, if verbose, oh, but I can't reference it before it's declared. C dot, this will be a, these are helpers. Where are the helpers at? Arg parsing. Verbose does exist up here. Okay. So I'm gonna have a little print verbose thing. Print verbose char star s, and void it up, and here we say printf %s, give it s, and we'll do a new line here, and we'll say only if verbose. There we go. And now down here, we're just trying to do the test. I can just say print verbose. Oops. And I'll give the string block bits. Let's do it as a printf verbose. That makes more sense. So here we have, what am I doing here? What did I want to print? I totally forgot. Oh, index. set index. And that's going to be %d new line. And we give it we'll have to do it as a macro. Let's do it as a macro. So this how do I adder? There we go. C sets indexed by adder is now what we return. Yeah, return that. Okay, and this printf verbose needs to turn into a pound define. Yeah, this guy here. We could do it like that. And then let's just be everything in here. You do a C macro with args. We'll just say args. What if I want to capture all args? Yeah, okay. Okay. Okay, let's build it. We're gonna need we got 7 minutes left. Okay, we got problems here. Those are notes. Let's go back up. Error, %d format expects int. Okay, 279 here. D expects type int. Type. Yeah, I did that. Did I not write it? Okay, now we have 307. One wrong there. Auto sim. Oh, unused variable sim. Because this is actually set. Select set, and we say set. Here, we'll just say set t pointer temp temp is equal to set. There we go. Okay, appears to be working correctly. Okay, so we selected the right set. Now we need to say, hey set, find upsert. I think it'll be like an upsert. Line, and we'll say give it the set and the adder, okay. We need now under the set, we selected our set. Under the set now we need an upsert line here. This gives us our set t pointer to s and our adder, which is a uint 64t. So here we're going to say for auto I is equal to 0, I is less than something, I plus plus. We iterate over every line. And if we look at the set definition, we have lines, so we can say s lines sub I. How do we know how many lines we have? So the set also needs to capture that lines per set. This needs to be s lines per set is equal to lines per set. Okay. So this is going to be S lines per set. So we go to each line and we say, hey, does the line match our tag? Not upset. insert. So this becomes an upsert line. Okay, and over here, where do we do our upsert? So we did our select set here, upsert line into the set. Okay, let's just go ahead and make sure it builds. Has a good get status get at all. It's a good stopping point. So I come back, the upsert line. So we've selected the right set for this item. So now we got to traverse the set and see if it's in the set. If it's in the set, then we record the hit. If it's not in the set, then we record the miss and we add it to the set, optionally evicting something. So all this logic then goes into this one upsert line. Ugh. It is kind of crazy that like I kind of default into this object-oriented programming mode even with C. Like I want to be able to better visualize memory and how to lay things out in memory so that my access patterns take advantage of spatial locality. But I think for the first draft of this, and because it's a simulator, it's not like performance critical. I'm not going to really worry about it. I'm just going to do it as object oriented. But I think that if I wanted to optimize this, I would go in and start looking at the memory layout, access patterns, and how to make sure that I'm taking advantage of spatial locality and temporal locality. And I want a project that like allows me to exercise that muscle a little bit, because I want to get better at doing that. I want to get better at thinking in that mindset. And there is a book that I might get around to reading at some point, which is like, I think it's a data-driven development or something. Data-driven programming? No. Data-oriented programming? I forget the name of it. Hawaiian Shirt Tech Conference talk. Red. It's like some dude in a red Hawaiian shirt. I actually have it in my learn log here. Learn log. If I go to talks, yeah, data-oriented design. And there's a book, data-oriented design. Why does Amazon not come up here? I think I also have that in my learn log under books. Data-oriented design, here it is. I'm not sure if that's the right book. If I go back to talks, this guy did a presentation on it.
Thanks. So, title slide. All right. Yeah. Anyway, so yeah, in order to get here, I watched some talks. I attended Handmade Seattle 3 times. Talked to a bunch of people, and then I read this data-oriented design book by Richard Fabian. But it still took me a long time to get it. Like, it just didn't click for a long time for me. So my goal of this talk is that if you're here, if you're where I was for this 10-year period of my life, I want to help you like get over it with me. Like if you have the same like learning model as me, maybe I can like help you just like fast forward, right?
So yeah, data-oriented design sounds like a stupid name, but it's basically thinking more along the sides. In the Go community, they call it machine empathy, I think. But it's basically like you want to lay out your memory in a way that you're accessing it so that it takes advantage of all of these like optimizations that are in the CPU for leveraging the caches. And object-oriented programming with pointers everywhere inherently is not that. And my default mindset is to do that, the object-oriented approach, and I want to get away from that. I want to get more close to the machine and how it prefers to operate. So this simulator was another good experience for me. I feel like it's significant. I haven't completed it yet, but I feel like it's a significant amount of code so far. I wrote all of this myself, and it's already at 405 lines. I think going back to the ePol file server, that would be another good project to kind of try to exercise my C chops, but kind of going more towards this mode of like mechanical sympathy, like thinking about how can I access memory in a way that is not jumping all over the place. So I'm going to leave it there because I got my MAT session in a few minutes, but I will be back on this evening for a couple hours, and hopefully I can wrap up. It's only that little bit of logic that I need to implement at this point, and yeah, hopefully I can wrap that up in a couple hours this evening and finish at least the first part of this lab. Cool. All right, I'll be on later.